Hello everyone, welcome to the presentation. My name is Prakash Chipa. Today I'm excited to share the work Möbius transform for mitigating perspective distortion in representation learning. This work is accepted in ECCV 2024. This research tackles the critical challenge in computer vision, how the perspective distortion affect the representation learning capability of the models, and how to mitigate the perspective distortion in learning to make the models invariant of it. So coming to the perspective distortions, it changes the shape, size, and orientation of the objects from its original identity. So you could see a couple of the examples here, like car, people, and the buildings. So the shape of the objects and orientations has been distorted because of the capturing angle and many different intrinsic and intrinsic parameters of the camera. So what are the basic challenges behind it? So one of the prominent challenges about the distribution shift causes by this orientation changes and shape changes of the visual concept in the images. And then in the last decade, the research focus has been on perspective distortion correction methods, uh, which at the first step correct the perspective distortions and then apply the computer vision task. So in this pipeline, it makes the whole pipeline as a two steps, which is compute intensive and not so efficient for the real world computer vision applications. And another thing about the perspective distortions that we don't have any explicitly dedicated data sets available to train our models because the camera parameters which causes the perspective distortions, be it intrinsic or extrinsic, are unknown to us, so we cannot estimate it. And finally, perspective distortion being a non-linear in the nature, the existing affine transformations, either they are linear or non-conformal, so we cannot synthesize the perspective distortion in the learning pipeline. So that causes the another challenge. So in this work, we focus on synthesizing the perspective distortions by understanding its basic scientific properties being non-linear and non-conformal, and we wanted to do it without knowing the camera parameters, as those parameters are always unknown to us. So one such theory from the mathematical complex theory in the mathematics comes from Möbius transformations. Möbius is a non-linear conformal transformation in the complex space, which is parameterized by four complex parameters. And and Möbius transformation being conformal preserves the angle between three different points during the transformations, which could be translated into the computer vision. That transformation can be carried out on the images while while the visual integrity of the image and underlying concepts can be still be preserved. So taking this Möbius transformer to our computer vision methods, we call it mitigating perspective distortion method. So the core part of the method comes from where we take the images, translate these images pixel to the complex space, and in the controlled manner we apply Möbius transformation by controlling the transformation characteristics by their complex parameters components, and after the transformation taking back the transformed image to the pixel level. So in this way we are able to synthesize the perspective distortion, as you could see the example of cat from a different orientations, left, right, top, and bottom. So once we achieve this mitigating perspective distortion method, then we integrated in supervised and self-supervised methods like Dino and SimCLR, and we have performed standard training using ImageNet datasets. And besides doing this representation learning on supervised and self-supervised settings, we also explore several real-world applications like crowd counting, object detections, fisheye view recognitions, and person re-identifications. So we adapted our methods MPD to these applications, as we could understand like crowd counting and object detection, the bounding box and the labels of the images also need to be transformed. And for the person re-identifications, we take recent methods called clip re-ident and integrate the MPD approach to showcase the effectiveness of the proposed method. And finally, for the transfer learning, to understand the transfer learning capacity of these models, we have also done the investigation on fisheye view recognitions. And since the perspective distortions cannot be estimated in journal because the parameter of the camera parameters was unknown, so there was no such benchmarks and dedicated data set was available. So in order to fill this research gap, we also developed a benchmark called ImageNet-PD, which is derived from original ImageNet validation sets. It has its own 8 subsets, which you could see on the screen. It's like 4 orientations with the left, right, top and bottom view, and their background padded variants also. And when we have done the investigation on existing models from different CNN and transformer architectures, so you could see the pattern that all the models are found to be not so robust against this newly benchmark, which shows that how the perspective distortion is challenging the representation learning capability of the existing models. Then we quickly talk to the about the results part. So when we evaluated our self-supervised and supervised models on different publicly available benchmarks, which has perspective distortion effects like ImageNet-X, E, and newly developed ImageNet-PD, consistently the models which are integrated with the MPD have shown consistent improvement. And to notice that by including MPD in the learning process, it has able to maintain the performance on standard data distribution on standard sets, whereas it significantly improved the performance on ImageNet-PD's subsets. Then we talk about the results on real-world applications. So coming to the crowd counting part, on the 3 different data set, it has achieved the state-of-the-art performance and by showing the performance improvement significantly. Similarly, the clip reident method, when it is integrated with the MPD method, it has shown quite a bit good performance improvement on both backbones, ResNet and VIT. Similarly, on the object detection, we are able to improve the performance from the baseline by 3%. And in the transfer learning capacity on the fish eye view recognition is also seen on VOC 360 dataset, where the supervised and self-supervised both the models are doing performance improvement. Finally, we talk about the contributions of this paper. So we are mathematically able to model the perspective distortion without knowing the camera parameters, which allow us to synthesize the perspective distortion in the learning process. Then we developed a dedicated perspective distortion dataset, ImageNet-PD, which could foster the research in this direction. And we have shown seamless integration of the proposed method in several computer vision tasks and applications and show its effectiveness. Finally, these methods provides a generalizability, transferability, and adaptability across the learning paradigms, as we seen in the self-supervised different methods across architectures and the applications. With that, I thank you everyone.